Let's get started. It's really weird for me to do this. I mean, I've done webinars before, but this is a Thursday night before a long holiday, and normal wisdom, of course, would be to never do an event at such a time, but these are not normal times. So, starting with the actual presentation, I hope you can all see the title slide that says the title and my Twitter handle. And one thing, and many things, and Stephanie mentioned some of them, but one thing I will be upfront with you, I'm not a Rust expert. I've actually programmed in many languages, also commercially for many years, but I'm not really programming commercially in Rust, and I'm certainly not an expert. But I do think that what I'm showing you tonight, which is an overview, a personal overview, and some of my first impressions from learning Rust and becoming a reasonably okay programmer in Rust, are actually probably quite helpful for you if you're also new to the language. Let's start with the why. Why is Rust a topic that we want to talk about? Some of you may have recognized this. This is the StackOverflow questionnaire, the survey that they're sending out once a year, and there's a number of different categories, and one of them is the most loved, dreaded, and wanted languages. What we're seeing here is the most loved language, and you can see Rust here sits in the top spot. Interesting enough, Rust has been in that top spot for 4 years in a row now. This is obviously the 2019 survey, and Rust is only out for 4 years. That is, Rust 1.0 was released in 2015. So that's quite an achievement. I would say that for its entire real existence, it was the most loved programming language. I think part of it is due to the excellent community. It's an amazing community. When I wrote a blog post, which was a precursor of this talk, it was so helpful what people responded and how enthusiastically they were helping. And I think this is really a sign of people really loving the language that they're working with. Loving the language is one thing. Let's look at the flip side. There's also a section talking about the most popular technologies. And if you look at that, I'll spare you the searching. Rust is much, much further down. It sits here at 3.2%. So there's a huge discrepancy that we are still seeing between Rust on the one hand being really, really loved by the people who are using it, but on the other hand, when you look at how far it has spread in commercial use, it is not that popular right now. It is just not being used. You can, if you squint, you can see, actually, you don't have to squint. You're sitting in front of computers and not in a big audience screen. You can see there's a professional developers tab also. Trust me, it doesn't look very different there either. So it is just not that hugely popular at the moment. Stepping back a little bit, think about what do these three companies have in common, Apple, Google, and Mozilla. All three of them have written a large amount of software in C and C++, and all three of them don't particularly like the experience, which is why all three of them have in recent years, and I include the last 5-6 years here, created their own new programming languages almost exclusively to get away from C and C++. Apple has created Swift, Google has created Go, and Mozilla has created Rust. They're all quite different languages. Comparing them is another talk in itself, so I won't do this. I will focus on Rust. But I will return to Apple briefly to further highlight why people are excited about Rust as a programming language. This is not specifically selected. These are the knowledge-based document accompanying an Apple security update. And as I said, I didn't specifically select it. This just happened to be the one that was the most recent one when I wrote the first version of this talk last summer. So it is not selected in a particular way to make my point. I think it is quite representative. And I'm not leaving anything out except 2 vulnerabilities at the beginning. They are ordered alphabetically. So if I look at this, it tells me what Apple fixed in the security update. And what we're seeing here is, in core data, there's a description, an out-of-bounds read was addressed with improved, a memory corruption issue, a buffer overflow issue, so 3 on the first page, memory-related problems. I'm scrolling down, and I'm seeing another 4 of them. All the ones that are marked with these pink arrows are memory-related issues. And again, I'm not leaving anything out. I'm just scrolling here. The next page looks very similar. Again, a large number of these problems that were fixed in the security update had to do something with security, sorry, with memory problems. So this is the Silicon Valley view. What about that large company from Seattle? I mean, I'm talking about Microsoft here. AWS, interestingly, also does some Rust in some of the high-performance parts of their cloud solution internally. But I'm talking about Microsoft here. Where are they at? Last summer, in obviously Visual Studio magazine, there was an article titled C++ memory bugs from Microsoft to Rust instead. So what we're seeing here is that Microsoft, of course, being quite far ahead, in the early 2000s came up with a language almost as a replacement for C and C++ called C#. It was more similar to Java, or is more similar to Java, and that really hasn't proven successful in the areas that C and C++ were successful. So while they created an alternative very early, this is not currently in the race. So for some of the more systems-related programming, they are eyeing Rust instead. This is not just because some engineer said so. They actually at Microsoft Research look at all their own security issues. And this is the summary. I'll let you read this. So what they're saying here is, they're saying the vast majority, or they're saying the majority, but I remember from the article, it's about 70% of vulnerabilities fixed that had a CVE, like a vulnerability report assigned, are caused by developers inadvertently inserting memory corruption bugs. So, and this is Microsoft. They have a long history. They have a big attack surface. They wrote a book writing secure code. They made a big focus. They have some of the best tools available, like find bugs and all the static code analyzers and so on. And yet, the majority of the problems that they have are related by memory-related problems. So there really is something that is beyond what most human developers can do. Personally, I had a slightly different journey to arrive here. And at ThoughtWorks, we are increasingly working with embedded software. That is where the software is only part of a larger solution, generally is some hardware solution that contains a little computer or a larger computer, as you can see one here. This is an NVIDIA Jetson board that is used by some of our clients. This is a developer board. The one that would actually be put into the devices is a different form factor, but the same thing. They're quite powerful. And again, we're thinking, okay, if you're starting to build something new from scratch, why would you repeat the pain from the past and keep doing this in C, C++, or even the transpiled MATLAB version, which is also not uncommon, I would say. In all fairness, I would say these boards in particular are quite powerful, and I know that some of our colleagues are deploying Docker containers on them, and they're writing services in Go also. But it was my motivation to think, if we are going to bigger hardware, if we're trying new things with embedded, why not also look at a new programming language? One company that is not a ThoughtWorks client, but is public about this is Alstrom, the company that also builds trains. They're also specifically, and have talked about it publicly, are looking into using Rust in such a context. Okay, let's get to the code, but not right to the code. Let's get ready for some of the code. It should really be said that introducing a new programming language, you should really build on the shoulders of the experience, the shoulders of the giants, of what other companies, other organizations have done before. And in my personal experience, from knowing and having programmed in many languages, Rust really got almost everything right here. So the first thing you need to do is you download a script that creates a Rust installation. The Rust installation can actually live in your home directory. After that, you have this command that I highlighted up here, the rust up command. And with rust up, you can update your entire installation of Rust on your machine. So really, it just, yeah, of course, it's nothing special, but that's, I think, a good thing. It just works, in my experience, unlike some of the other environments that I've seen. Once you have Rust on your system, it also comes built in with a package manager. This one is called Cargo. The names, by the way, will not help you. Googling for Rust and Cargo when you have issues will give you lots of other things, because Rust and Cargo are obviously commonly used terms in the English language. So that is a bit of a downside sometimes, but never mind. So Rust is the tool that you will use to build. It manages your dependencies. It allows you to create scaffolding, as we can see here. So here I'm saying Cargo, create a new scaffold, and the name of the software product I want to build is called Hello Rust. And what it creates is absolutely minimal. Main.rs is the main programming file, like main.c or Java or whatever, and cargo.toml is the file that describes the product as well as the dependencies. It's a bit like package.json or the Gradle or Maven files that you may know from other programming languages. What I have decided, I was asked to do this as a presentation at a conference by somebody who I know, and he asked me whether I could do this Rust introduction. And I thought this is really going to be quite tough, because Rust as a whole is a large programming language compared to some of the others, for example, like Go. Go could always be seen as a simplistic language that is easy to learn. Rust, on the other hand, is quite large. I thought, how can I do this? How can I do this justice? And it's really tough. At the conference, I tried to do it in 45 minutes. Today, I have the luxury of having an hour, plus time for questions if you want to stay around. But still, it is not easy. So I thought, how can I do this? And I really did not want to do a hello world. So what I did instead, I took a piece of software that I wrote when I wanted to learn Rust myself. This is a hobby project. I had written this, and I'll come back to this much later in the talk, in Clojure originally, Clojure being the Lisp dialect on the JVM. It is a piece of software that simulates agents. It's a combination of genetic programming, genetic algorithms, but really specifically genetic programming and artificial life. These agents are running around in the world. They're bumping into each other. They have a strategy. The strategy can be something like turn left, go ahead, look around, eat some food. They have to eat food to survive. When they bump into each other, they create offspring, and then genetic programming kicks in, and the strategy that they have is then going through a genetic programming algorithm that creates the offspring with a new one. This is basically what you need to know about the sample code. It is quite nice because you don't have much UI, you don't have much I/O. This is really about computation. And the idea really is you have some agents running around in the world, and they have strategies expressed as a little mini program, and there's some genetic programming to, you won't even get into the details of that, some genetic programming to create offspring. If you've noticed it, I'm actually using IntelliJ here, which many of you, if you do know it, probably know it as a Java IDE. Normally these days, Visual Studio Code is my go-to editor, IDE, if you will. And I actually tried Visual Studio Code at first, and it was a good experience for using Rust. Luckily, I also have a full license for IntelliJ, and I tried that just because somebody told me, and I personally found that I was even more productive inside IntelliJ. Even though, as I said, JetBrains has a number of different IDEs, but for me, the features were there, and the features worked really well. Not everything works as well as you would expect it. Inlining code, for example, the refactoring, the automated refactoring doesn't work or doesn't work quite well. But on the whole, I found it a really, really good experience. What is also interesting, what you can see here is in the declaration of dependencies further down, you can see I'm declaring a dependency on something called Chrono. Chrono is a date time library. Rust, despite being a large programming language, went to, in the same approach that JavaScript and C went and did not include a big standard library. So even something like date handling is an external dependency. You could use different date libraries than Chrono. At the moment, that is the go-to one, which I found out after reading a couple of Reddit threads. You can also see a little bit further down in line 10, the random number generator is also an external library. And also interestingly, in line 11, cert, the serializer, deserializer is also an external dependency. What is even more interesting here is you can see in the following lines, I'm declaring dependencies on cert JSON and cert derive. That means even the dependencies are quite modular. I can only create serialize and deserialization without having to use JSON. One of the reasons here is obviously that Rust, and I didn't mention that so far, compiles into a single binary. It includes everything it needs to run. It doesn't have to have an environment installed. It's a self-contained binary. And of course, you want to make the binary small. It's easier to transmit. It's easier to roll out. At the same time, it is also decreasing the attack surface. If you have less code, possibly in your binary, you have less possible attack vectors. What is also interesting, the last line here, if you look at UUID, I say I want to generate UUIDs, and some of the libraries know each other. And you can see here at the end of the line that in UUID, I'm saying explicitly, I want two features. I want the version 2 UUIDs, and I want cert. So what I'm saying is UUID library, I want you a feature to deserialize and serialize UUIDs. So you can even work on that level. You can create features that projects or products that depend on you can choose to use or not use. Again, all in the name of creating small binaries, of creating the amount of code that needs to be included in the deliverable. One last thing that is worth mentioning is in line 5, I can explicitly specify an edition. And here I'm saying I want Rust edition 2018. I breathed a sigh of relief when I saw this after my experience with Swift. Apple with Swift also created a language that is evolving over time. I think that's the right approach, but Apple really created a whole mess for the developers. If you are now checking out code in Swift that you last touched 3 years ago, I did this last year, you cannot even compile it in the current version of the IDE. In one case, I had to go to an older version of the operating system. With Rust, they have really made clear steps of editions. You can select them and you can say which edition you want to target, and it works with today's toolchain. So they evolved the language, but they preserve this backwards compatibility, which I personally believe is, again, another small thing. If you have never seen anything else, you think, yeah, that's how you do it. But it is in contrast to what other languages are doing. So very quickly, Cargo builds the application. You can see this is running, and you can see if you've worked in compiled languages, in really compiled languages, it is not super fast. I mean, this is running on a MacBook Pro. It's okay, but it's not super fast. I mean, the good thing, of course, is it supports incremental builds. That means, of course, that if I make a change, only the pieces that I have changed need to be recompiled. If you want to do a release build, an optimized build, that will take a little bit longer. What you also might see is now this is the build for the toy project, for the hobby project I talked about. You see there's not that many dependencies. This shows you also the transitive dependencies. This is slightly deceptive. The moment you include a web server, this looks much more like an NPM build. You literally get hundreds of dependencies, of transitive dependencies. This is only because it's a small project. And one last thing, these dependencies, they're all compiled because I'm compiling everything to a single binary. That means if you look at the target directory in which everything is assembled, these can be quite big. If you're doing regular backups of your machine, please exclude them from the backup. You'll be backing up gigabytes of binaries that you really don't need because then they can be recreated, obviously. So, cargo testing is, of course, a first-class citizen. One thing that is quite curious is that the tests are included in the same file that the functions and methods that you're testing. So rather than, like in Java and other languages, being in a different directory, they're included in the same source code file. Took me a while to get used to. I can now see that it's a viable way of doing it. I know, it's just much of a muchness, I guess. What you did see, if you looked, running the test is actually quite fast. It is faster than the terminal can scroll through. And the combination of incremental builds and the really fast execution of the unit tests really was working well for me. It never got me out of the flow. I'm quite sensitive to this. I really do test-driven development. I love doing test-driven development, and I'm sensitive to being interrupted, to be pulled out of my flow. But again, even though the compiler probably doesn't look that fast, when you're actually working in it, you're making small changes, that red-green refactor flow that you have in test-driven development really works very well, at least for what I've seen so far. So, 15 minutes into this, let's have a look at some code. First thing, if you look at this, and it's the first time you've seen Rust, maybe you notice a certain tendency for brevity. Almost everywhere they abbreviated the words. You can see pub instead of public, fn instead of function, impl instead of implementation, u64 for unsigned 64-bit integer. And then similarly, you see struct and impl. Interesting here is, even though I will talk first about the more object-oriented aspects of Rust, it really isn't an object-oriented language. You can see here, I'm declaring a structure, the world structure, which is the structure in which these agents, the little creatures, live. And that could be it. It's like C. It's a structure that can exist. I can almost attach, and I'm putting these air quotes around it, attach implementations to it to create something that resembles a class in other programming languages. And this is what we're seeing here. In the bottom half of the screen, you see impl, world, and now I'm seeing, there's of course more further down, I'm seeing methods, if you will, that are related to the structure I've declared. But the structure can stand alone. You can just create a structure in memory. Other things that are noteworthy. Rust does have an option type. Hooray, no more null pointers. So what I'm saying here is this name of the world is an option of a string. So it can be, second line, it can be none. This is the actual Rust code. It's saying there is nothing in here. There's no name given. Or I'm saying some, and then I can say my first word. This is almost identical. It totally reminded me of Scala, of how Scala is doing it. And I will show you later that there's a lot of syntactic sugar in Rust to make working in that way quite nice. You have to always unwrap it. This here shows you the first declaration of a function. You see it's a public function. Its name is new. We see it has two parameters. One is called name, and its type is %str. Ignore this for the moment being and assume it is some other thing like a string. There's a reason why it doesn't say string. The second parameter, confusingly, is called params, and it is of type params. I apologize, but that was just the way it is. This is when I'm creating this world, I'm passing parameters in it, like how big is the world, what is the shape of the world, what are other parameters of it. So these are being passed in. Then we see this arrow-like notation that is also probably well known from other languages, and the return value of this function is world. So I'm specifying the input and the type. This is the syntax, I think nothing specific here. This, though, I should say, is just a convention of how constructors or constructor-like functions are written. This is just what people happen to do. This is nothing specific to the language. The actual construction of an object or a structure looks like this. There's a special syntax for it. I'm writing the name of the type, and then in curly braces, I'm giving the values of all the fields. And what you notice is I have to specify all the fields. I can't just omit something or rely on some random initialization. What is interesting is what we see here in the lines that I've marked now. So random is assigned RNG::new. So we're seeing I'm using the same convention for constructing a random number generator. And at the bottom you see log. I'm also creating a new thing that the world can log events into. What is also interesting are those two lines here, params and terrain. There's a shorthand. I could have written this. I could have written terrain::terrain, because what I want to assign to the terrain field in the world structure is the local variable terrain that is declared in line 26 further up. What Rust does let you do is if you would write terrain::terrain, you can just write it once. I'm highlighting this because this is a design choice I noticed in Rust. They have added a fair amount of extra syntax that is confusing for beginners. So that is what people call a steep learning curve or harder to learn, but it is good for readability in the long term, because here you can't make a mistake. The intention is clear, it should be the same one. I can't make subtle spelling mistakes, it's more concise, but in the end, it is a little bit more hostile to somebody who picks up the language, because it is more things you need to know about the language. In all fairness, when you write the code, you can write terrain::terrain, and the compiler will certainly accept it. It is only when you read somebody else's code that you're thinking like, what is going on here? And this is one of a fair number of examples where Rust has these nice shortcuts for the experienced developer that may be slightly confusing for people who have not programmed in Rust before. So, moving on, here's a very simple implementation. This is a method, if you will, in other programming languages. One thing that you might notice, well, what it does, it runs a number of simulation cycles of the world. What you have to do is you have to pass in self. This is a bit like in Python. Explicitly, a parameter called self is passed in. It's somewhere like Objective-C where it's hidden, but it's also passed in. But here you have to be very clear, self is passed in. And that is actually the indicator what differentiates a function that stands alone from something that would be considered a method. For now, ignore this modifier there, the %mute. We'll come back to that later. And then you see a second parameter is num. Here, obviously, the number of cycles that the simulation should run. And it is an unsigned 64 integer. Rust is quite specific about the number types. They are signed and unsigned, they're in 64-bit, in 32-bit, they're size T, and so on. And they're all not assignable directly. You will really have to cast them. Again, this is done to write semantically correct code, but it can be somewhat annoying when you're coming from environments where the numbers are all the same. And normally, maybe unlike in JavaScript, but most of the time, the environment does the right thing for you. You'll be like, yeah, of course I can assign this. I know this works. What we also see is a lot of modern constructs here. You see the underscore in the for loop where I'm iterating up to the number. I'm putting an underscore in here because I don't need the variable. If I would call it I, the compiler would warn me that I have a variable that is not used, and I can use the underscore to signal throw it away. We also see with the 0.num that ranges are first-class type. They're not just a random structure, they're really first-class part of the language. Now what I can see then in the next line, I can just call another method on myself, do one cycle. And that makes this a nice example because this is so easy to understand. Even if you've never seen Rust, this is very, very clear, I guess. So let's get to more complicated. I'm going to step it up to a point where it's going to get uncomfortable to you. So this is a function here, a utility function that I'm using to count the cycles of a program. So I'm passing in the world parameters. Remember I mentioned them before that define the world and the simulation, and I'm passing in the program, which is basically an array of instructions. These instructions, this is from a different part. This is actually from a parameters thing. This is the definition. You can see a command like eat that takes 10 of these virtual cycles, and the move command takes 5. And at the bottom you see branch food ahead. So if food is ahead, then branch in the program, that costs 1 cycle. Interesting to highlight here is, this is of course a hash map that I'm declaring. Rust does not have literal hash maps. Where does this come from? You probably didn't notice it. In the dependencies definition that I showed you in the cargo.toml file, there was a reference to something called maplet, literal maps. And Rust has a macro system. And the macro system is powerful enough to change the syntax to introduce a feature like this. So this hash map bang invokes in some special way the macro system that it allows me to have now literal maps in the language when the Rust programming language doesn't have them. This is actually really difficult for the IDE programmers, and as you imagine, both Visual Studio Code as well as IntelliJ don't really support this. They do some basic highlighting based on the types that they're seeing, but they can't understand it because it's not normal Rust. But again, as a language that is designed for large programs also, this is quite powerful. These macro systems that we learn to love from other programming languages are really, really good to create internal DSLs and all sorts of other extensions, higher level abstractions, and Rust is quite good here. So going back to this, so this cycle count function is meant to add individually the count of the instruction cycles that each of the commands take. What I'm showing you here in the next line is now more a functional side of Rust. So proc, and you saw that I'm also getting used to all the abbreviations that Rust uses. So proc, I'm using an iterator over, I'm saying iterate over this, and then I'm using a simple left fold as it is known very theoretically in many programming languages. So the iterator uses a left fold. I'm passing 0 as the accumulator, as the initial accumulator. I'm starting with 0. And then the fold function, of course, will successively call this anonymously declared function for each of the instructions that is in the program array. And you can see now more syntax. You can see the vertical bars. They declare the parameter list of the anonymous function. It gets passed in the accumulator, the current instruction, and then I'm saying I'm taking the accumulator from the parents, I'm getting the count of instruction cycles for the current instruction, and of course, with successive call, this is adding everything up. And I didn't mention this earlier, Rust doesn't really use return statements. The return value of a function, in this case an unsigned 64, is simply the result of the last expression in the function body. And again, Rust has sugar, or not only syntactic sugar, but also different ways of doing the same thing. And of course, this is very common, what I did up there. I don't want to program a basic left fold myself. I'm just mapping something. So now it gets easier. I'm using the map function. I'm basically mapping each instruction to its cycles. And then at the end, you can see I have another built-in function where I can sum up everything in this new temporary array that contains the number of instruction cycles. So there's a lot of convenience functions again and again. This is something that once you know it, you love, but if you don't know it, you're probably cursing a little bit. So I talked a lot in the introduction about memory management and why this is drawing a lot of people to Rust. And there's really something special because Rust neither has a garbage collector, nor does it make you manage memory manually. And I was corrected by Brian Wirtz on this. They didn't invent it. It was known in academia, but the people behind Rust were the first ones who actually made this new concept called a borrowing concept, like lending and borrowing, commercially, or not commercially, but viable to be used for practical purposes. And how does it work? Rather than trying to shoehorn this in the application, I'm basically showing you the direct examples from the Rust book. The Rust book is a book that you can buy, but it's also a website that you can read. And it's quite good to learn Rust. It's a good resource. What we're seeing here is I'm declaring a string, and this variable s now owns the memory hello, the string hello. And as long now as the variable is in scope, the memory to hold the string is held in memory. The moment s goes out of scope, it disappears. The system will reclaim the memory when the variable s goes out of scope. So far, so good. What happens if I do the following? And whatever is highlighted in red will not even compile. So what I'm doing here is I'm creating a variable s1 that owns the string. And now I'm saying let s2 equal s1. So I'm trying to, or I'm assigning a reference to the string to another variable. And what would happen if s1 goes out of scope? Can I free the memory? Can I not free it? Do both of them have to go out of scope? It's really not a good situation. So what the compiler decides to do, or the designers of Rust have told the compiler to do, obviously, is that the ownership transfers. So after I've done this, s1 is invalid. And then it would give you an error message on the last line when I'm trying to print s1 after the ownership has been transferred to s2. I cannot use s1 anymore. Now, what happens when I call functions? If I was passing s1 directly into the calculate length function, I would have an immediate problem. Then the outer piece of code that I'm seeing here would not have ownership of s1 anymore. I would have the length of the string, but I wouldn't own the string anymore. So that really sucks, and that is not a good way of approaching it. So what I can do is I can pass a reference into the function. And for those of you who know C or C++, the ampersand symbol is used to create references, as you would in C and C++. What happens in here now, inside the calculate length function, s is now not a string anymore. You see it's a different data type. It's a reference to a string. So at the end of that calculate length function, when that variable s goes out of scope, the reference to the string goes out of scope. But the string itself was never owned by the calculate length function. It remained owned by the outer piece of code, and therefore it remains in memory. For those of you who look confused, which I can't see because I can't see everybody on screen, if you have not done more systems like programming in C and C++, this is really kind of what happens, except not really. So this is just for illustrative purposes. This is not how Rust works. This is not how C works, and it's definitely not how Intel CPUs represent memory. But it's close enough to explain it. So what we're seeing here is a memory dump. On the left-hand side, you see the addresses. Then you see in hex the actual bytes, and on the right-hand side, you see the same bytes as an ASCII representation. So when I'm doing let message equals get message, now message owns this block of memory that I've highlighted here. These bytes, and then of course on the right-hand side, the ASCII representation of that. What happens if I do this when I'm creating a ref to a message? What does that actually do? If you program in Java only or in these languages, there is no difference. It's the same thing. But here, a reference is different from being the real thing. So what it really means is the reference here is only these 4 bytes in memory, 006, 9674. And if you peek, that's conveniently the address of the blue box in memory. So the message ref also takes up some space, but it really only points, and that's what we call the pointers in C and C++, points at the location in memory. That means when message ref goes out of scope, only those bytes circled in pink go away. When message goes away, the entire message, all the blue bits go away. And again, this is not how it really works. They would not be on the heap and so on. That's a whole different thing if you know this stuff. But the idea, I think, is clear. The ref is a very different, it does exist. It exists somewhere in memory, but it's a different thing than the actual bytes of the message. So, other things you can do with your evil programmer hat on your mind. So I'm taking a reference to S and I'm passing it to this function. I'm only giving change a reference, but I'm trying to change the string by pushing something to the end of it. The compiler will not let me do this because the outer function only gave the change function a reference, but didn't allow it to change anything. In order to be able to do that, I need to be explicit. And this is another key concept in Rust. First off, I need to say that that string is mutable in the first place. So you see let mute s in the main function. And then even when I'm calling the change function, I can't simply pass a reference to s. I have to say I want to pass a reference to the string that the function that gets the reference is actually allowed to change. So I'm saying &mute. And after that, the compiler is happy. So what happens if we think this further? What if I'm creating two mutable references? Compiler will not let you do it, because we all know creating two mutable references, you can keep them around, you can pass them to a different thread, and the behavior of your program will get really, really difficult to reason about. So the Rust compiler will not let you do it. You cannot have two mutable references. You can have two immutable references, as is shown as the bottom. I can do R1 is a reference to S, R2 is a reference to S. Both of them are not mutable. And I can pass them to different threads because the compiler keeps track and makes sure that all the references that exist are mutable. That's really quite nice for performance reasons because you don't have to copy anything around. But the moment I'm trying to create R3, then a mutable reference, the compiler says, you cannot do that. I've already handed out immutable references. So the rule clearly is, you can have as many as you want immutable references, or, and a strict or, one and only one mutable reference. This is quite cool. I mean, I didn't mention it earlier. There's a security ISO standard for the automotive industry. And at the highest safety level, it says you can't even pass anything by reference. They say you're not allowed to do it because they know we programmers always get it wrong and can't reason about the code. In Rust, the compiler can do this for us. And it would allow us to actually pass references because the compiler can check whether it's safe or not. And then, last but not least, the third problem that we often see are so-called dangling pointers. So what I'm doing here is, if you look at the function aptly named dangle, I'm creating a string s in here, and I'm trying to return a reference to s. But the compiler is obviously smart enough to see that there's a problem. At the end of the dangle function, s goes out of scope. Hello, the memory would be reclaimed, but I've returned a reference. So if you think back about the previous thing, I would still have the pink bit pointing at the blue box that contains the memory, but the memory is reclaimed. And this is the dangling pointer problem that is a huge issue. And again, the Rust compiler can detect this and will simply stop you from using something like that. So that sounded easy, right? Let's have a look at some real code and show what that actually looks like. So here we have a function that I took from the terrain class. That is the actual modeling of the terrain the creatures run around with. This class is it's a method, and it passes in a function that is meant to be executed for each creature that sits in the terrain. What we can see here is there's this ominous f in there. So I'm passing in the function that is mutating, and the type of the function is plainly f. What does that really mean? I thought we had said that Rust really is quite specific about the types. The thing why they did this is because it gets too confusing. It is similar if you know C#, where you can also draw out these generic types and explain them in the next line of code, or in the next phrase, if you will. So really what we're saying here is the function the function called func that you're passing in here is a function that takes a mutable reference to the terrain, a mutable reference to the actual creature. It takes a tuple, they're also first class, 2 coordinates in this case, where the creature sits in the world, and the return value of the function is an option of a tuple. And the semantics here are, if the tuple is some, it is the new position of the creature. If it's none, the creature has died. So what we're seeing here is I can pass in a function, and I can declare quite specifically what the function does. So far, so good, I hope. So what happens when I'm invoking the doWithCreaturesMutable function in terrain? This is now code from the world. This is a small piece of code in the world that says process all the creatures. And what I'm doing here is, the world knows its terrain, and I'm calling the doWithCreatures function, and I'm passing in an anonymous function here that adheres to the specification you saw on the previous slide. So it gets passed in a terrain, a creature, and a position. And then it does things. This is now being called for each creature, right? You can see in the first line, it decreases the energy points the creature has to simulate some form of metabolism. And then the easiest check is, if the creature's age is larger than the creature max age, then we're turning none, the creature dies. Or if the creature's energy points are 0, it also dies because it is starved. What happens in this case, though, if you try to compile this, I'm not sure whether you would have guessed it, this does not compile. The compiler gives me this error message. This is the actual error message, including all the ASCII art and everything else. The compiler is really trying to be super helpful here with the ASCII art, trying to explain to me what has gone wrong. By the way, the errors are numbered. You can see that at the top left corner, there's error 0501. That's the one I'm triggering here. And the IDE puts a hyperlink in. It's quite cool. You can click on that, and it will take you to a page on the website that explains the error message in more detail. Or if you so want to, at the bottom you can see it says you can call the Rust compiler Rust C and get a deeper explanation of this error. But what happened here? And what does it try to tell me? It says closure construction occurs here, a borrow occurs, and another one. What is the problem really that it's trying to do? This is the code we saw earlier. What is happening here is inside this function that I'm passing to the terrain, I'm in the world now, remember, I'm using self.params. But I'm also further up saying self.terrain, and the terrain can mutate, which means it can change the state of the world, which means I shouldn't really pass out further references to world because I don't know whether world will not be changed. And this is exactly what the compiler told me. The closure that I'm passing in requires unique access to self, but it's already borrowed because the moment I did self.terrain, I'm also borrowing a reference. And this gives you a glimpse into how complicated these memory rules can be. And I mean, of course, I picked a complicated example, but what I wanted to say is while the rules are simple, the impact on programming is profound. The solution is also simple. In my case, I know that the two things I wanted here, the maximum age or the parameters, and the cycle, the number of steps the simulation is in, are not changing while the closure is being used. So I can just pull it out into local variables up here. And now, of course, the closure can reference local variables, and I can use params and cycle, and the compiler is happy with me. Because now the closure that I'm passing in has no reference to the world anymore. It has local variables that the compiler can easily capture, and if necessary, could keep around as long as the closure lives. This sounds simple now. It took me a while to understand this and to get into the flow, and you might also curse the borrow checker at first. But it really, really provides a huge amount of value because it eliminates whole classes of problems that you would otherwise struggle when your software is deployed in the field. Here, you're only struggling when you're sitting in front of the computer programming. Which brings me directly to the next topic, parallelism. Remember, actually, let me go back. I said I wrote this simulation, and when you do simulations, you want to run many of them. In this case, tens of thousands of simulations. I didn't even know the right world parameters. In modern day machine learning, we would call them hyperparameters. Like, is the world a torus? Is it a square? What is the best max age? What are the instruction cycles for each thing? I didn't really know. It's a huge error. It's a huge a huge space of hyperparameters. And I didn't know where they were, what were even viable ways to running these simulations. So what you normally do is you run a Monte Carlo simulation, you create certain brackets of values, you create random values, you run the simulation with random values and see which ones work. So you want to run tens of thousands of simulations. And this is exactly where I stopped with this experiment when I did this enclosure, which will become apparent later. It wasn't fast enough. But the good thing with Rust was, the machine that I ran this on has 8 CPU cores, which meant I could run this in parallel. I tried briefly to run one simulation in parallel. That didn't make much sense because the simulations don't take very long to determine whether they are viable or not, viable sets of hyperparameters, and the coordination overhead, because the creatures can see each other and so on, that was just way too high. So I'm basically just running one simulation on one core, another simulation on the second CPU core, and so on. And I needed to make no changes because the compiler had made sure that my software was thread safe and no memory issues occurred. So this is how I did this multiverse function. First off, Run multiverse now runs many simulations at the same time. I'm passing in here, you can see this at the top, I'm passing in a function called the world function that when I invoke it, creates a new world. You can see it's a function that takes no arguments, no parameters, and always returns a world. And here you can see I can actually inline the declaration. I don't have to use an F and declare it on the next line because the signature of this method, or sorry, this function is so simple, no arguments and just a return value. So what I'm doing in there then, I'm iterating over the number of threads and as many threads as I want. I'm spawning a new thread. You can see that in line 26. What do I pass into the spawn function? I'm passing an anonymous function. The double empty bars are nothing special. It's just an empty parameter list. And then in the curly brackets, you see the entire body of the function that I'm passing to the thread that I have just spawned. And what it does, it iterates over all the simulations I need to do. So number of simulations is the total number of simulations. If I'm running them in many threads in parallel, I divide the number of simulations by the number of threads, and that gives me how many simulations each thread should run. And then I'm just saying run world with the thread number, the simulation number, and the world function. And then, of course, the world function here has the round brackets, which means I'm invoking it here. So the world function creates a world, and that is passed into run world. As simple as that. What is quite cool is there's this keyword in the beginning called move. And what that does, it transfers the ownership from the thread that does the spawning, the main thread, into the subthread that the actual function runs in. So again, there's a very clear way of handling ownership in a scenario with multiple threads. Normally, you would also create a communication queue between the two threads so they can talk to each other and can send messages back and forth. That again is the topic of an entire talk. But in this case, it is so simple, I don't need to do that. The last thing I want to show you briefly is something simple, but also something that shows you how nice the syntactic sugar works. So here, thread spawn returns a handle called h. And I'm storing these handles in a vector. A vector is similar to an array, has some subtle differences, but like in many languages, an array vector, like a serial collection, I can, of course, misuse as a stack. So I'm pushing the handle onto this handle's stack, if you will. So far, so good, right? What do I want to do at the end? At the end, I want to terminate cleanly. So basically, I need to wait until all the threads have finished, and I need to collect them. And when the last thread has finished, the program should exit. And this is how I do it. So the handle that is pushed into the handles array in that line is later on popped from the stack. And here in this line, line 34, you see coming together a fair amount of nice syntactic sugar. So handles.pop, what is the signature of a pop method? Because it can do two things, right? It can return the topmost element from the stack, but somehow it also needs to be able to signal that the stack is empty, that I have taken all the elements off. In many programming languages, you would return null as a signifier that the stack is empty. Remember from the beginning, Rust does have option types. So what it will do is it will return a sum of a handle as long as there's something on the stack, and it will return none when the stack is empty. What Rust can also do, and you can see this here subtly, it can use this deconstruction that most people, I guess, these days know from JavaScript. So I can write sum in brackets h, and this will only match if there is something on the stack. If there's none on the stack, sum of h won't match. But it destructures it, sorry, I'm using the wrong word here. It destructures it, and after that, sum of h actually is not the option anymore, but the actual handle. If the stack is empty, the destructuring doesn't work, the let doesn't work, and the while loop then knows it needs to finish. So you can see how this comes together. The pop thing returns an option, and the while loop can finish because it returns none. The let, together with the destruction, works to allow me to access h without having to unwrap it. That there's another unwrap in the line is a different artifact from something else, but I can use h immediately. This is something that we've seen in Lisp. Swift offers something similar with the while let. but it's definitely something that I first saw in the Lisp family of languages, where you can make basically a little bit of an if statement, but then assign a different name to something based on whether that if was true or not. Okay, this is basically all I felt I should show you in 45 minutes to 60 minutes about Rust as a programming language. Let me spend 5 minutes on closing remarks about performance. What you are seeing here, and I'm not sure how well that works over Zoom, this is actually a screenshot or a video shot of the simulation of the closure version. And you can see the agents running around, and the green bits are the nutritions that they can eat. And you can see them run around, and sometimes you can see new ones pop up. It's actually harder to see on this one here. The closure version did about 110,000 cycles per second. That is like, if one creature did one cycle, that counts as one, not 110,000 cycles over all creatures. So 110,000 per second. That sounds reasonably fast. But if you think about the number of creatures on this, if you think about the fact that you want to probably simulate 1 million cycles to make sure that the hyperparameters are okay, and then you want to run like 10,000 simulations in a Monte Carlo simulation, then that can become quite burdensome, and it would take weeks to run this. And also the closure version didn't work that well across multiple CPU cores, mostly because I wasn't as disciplined with the code, because the compiler didn't push me to be disciplined. So what I did then is, I basically transferred the entire program into Rust. And I did this really by copy-pasting the acceptance tests from the closure version, making sure that they were then compilable Rust code, and then implemented the acceptance test. So I'm reasonably sure that when I did this comparison, the two simulations, the closure and the Rust one, did actually do exactly the same thing. But as you can see, the Rust version at 3.5 million cycles per second was significantly faster. This was roughly based on the experience I had, what I was expecting. I hold the JVM in very high regard. I think it's a super good Java virtual machine, sorry, a super good virtual machine implementation. There's a lot of really cool things. I know of high-frequency trading applications implemented in the JVM. It is not a sloth, it is actually quite fast, but when it comes to something like that, of course, something that is compiled into machine code will generally have the edge. And we should also not forget, I was programming this in Clojure and not in Java. In Clojure, I did this, I'm a reasonably competent Clojure programmer, I would say. I did this in an idiomatic way, which means the agents basically were more or less like dictionaries. And in Clojure, things are immutable, so when I want to change the state of an agent, I have to copy parts of the dictionary. Clojure does that very efficiently, but obviously not at the level that you can get from a language which can change bytes in memory. One thing though, I realized at some point, I should probably do a release build and not the debug build. And this is the number I got then, 25 million cycles per second. So this is the change I got from going from a debug build to a release build when the compiler did some optimization. And the cool thing here is Rust uses the same underlying tool chain that also Swift and the C-lang, or its Clang basically, the C compilers use. So everything that comes after the translation into the low-level virtual machine code benefits from all the optimization Apple does for the Swift compiler, as well as all the other things that are done for C and C++, because it is the same compiler backend, which gives us this optimization, or this degree of optimization and that level of performance. One thing I do want to highlight though, when I profiled, and that was actually not that easy. I'm really spoiled from Java when it comes to profilers. When I did do some profiling on the Rust code, I realized that it was spending 50% of the time in the random number generator. And Rust tries to be safe by default, and the random number generator that you use by default is producing cryptographically sound random numbers. I didn't need that. To decide whether the creature turns left or right, I didn't need the same level of rigor that you need for cryptography. So I changed to a simple, I think it was an XOR shift random number generator, and brought down the percentage of time that was spent creating random numbers. That, of course, made Rust faster. I didn't do the same optimization in Clojure, but I don't think it would have made a huge difference. Is this just anecdotal? Is it just me? I can't draw in Clojure. Is it Clojure being super slow? I don't know. I don't want to go out here and say I have conclusive evidence that Rust is faster. but I want to leave you with another anecdotal piece of evidence. And this is from Brian Cantrell. He writes dtrace, that's a tool in Solaris, also used on macOS, to actually trace system calls. And he's wrote something, this is his blog post, if you follow the QR code, you get there. He had similar experiences than I guess. He had some frustrations trying to implement this because of, I guess, the borrow checker. So he gave up on performance. He just said, I just want to get it to work. And what happened when he did this? Well, actually, let me go back. What he did is he wrote a piece of software to generate state maps for traces. And the example that he gave in his blog post were 229 states and about 4 million transitions. The original version he implemented in Node.js took 83.1 seconds. And that was unacceptable to him. And I always make this joke at this point. Whoever says Node.js is blazingly fast has generally never programmed anything but Node.js. Sorry. So what he did is he wrote a hybrid. So he basically wrote the inner loop in C and then used the native interface in JavaScript to invoke that loop. So basically 99.9% of the processing now happens in the C programming language, and JavaScript is just the glue around it, if you will, that calls that C function. And that brought down, I would argue, the compute time significantly to 11.8 seconds. So now remember, he knew this code, and that was the code Brian was translating into Rust. And he also, like I, struggled with the borrow checker. I'm sure he saw all these error messages that I showed you and was getting frustrated and said, let me just get this to work. And this is where it ended up. It was actually faster than the C version. He dug into it. He's more like a low-level kernel type of guy than I am. And he looked a little bit at the code. He said, how can that be? How can the Rust code be faster than the C code even? And he saw something, how the emitted machine code was making more effective use of the CPU. I'm not sure, I mean, I know a little bit about CPUs, not that much. They're really complex beasts these days with branch predictions and things they can do at the same time, they can't do at the same time, and so on and so on. And it really looked like the Rust compiler, the way the low-level virtual machine code that was emitted by the Rust compiler it was possible to translate it into code that was more friendly, if you will, to the CPU, and then in the end resulted in a higher execution speed. Most of the benchmarks, and as we all know, benchmarks are really, really tricky topic, which is why I'm shying away from trying to make any absolute statements. Most of the benchmarks show you that Rust really ends up at a performance level that's really comparable to C, and not this blazingly fast something, and I have a micro benchmark that shows something. It is really on a large scale comparable to C code, while at the expense of a little bit of pain at compile time, gives you much, much safer code in the end. So, with all that said, thank you. I saw flying past in the Zoom chat some questions already. But what I want to do also today is a little experiment, and I've prepared the following. I don't know whether you've seen it before. I've only learned about this a while ago, a tool called Slido. So, if you wouldn't mind, take out your mobile phones, scan the QR code, and open the web page. It doesn't download an app or anything. It just brings you to a web page. And what it should do is, if you scan the QR code and open it, it should get you to a page that has two tabs, one called Ideas and the other one called Polls. And let's do the poll one first. And what I've asked you to do here is, this list scrolls a little bit, and tick the 3 programming languages that you use on a weekly basis. Which are the programming languages that you, who are listening to this webinar now, that you are using? And I will show you the results, obviously, in a minute or two. What you can also do in parallel, when you're bored or when you don't care about the question that I'm about to answer, you can go to the other tab, the Ideas one, and you can answer the question that is highlighted there, which is, what do you want to do with Rust? Why did you come to the talk today? Why are you interested in Rust? Do you have something specific in mind that you want to use Rust for? And we'll see. And as far as I've seen this in Slido, you can comment on each other's ideas. I think you can even upvote each other's ideas. So this, to me, is an experiment. I've participated in a call or in a webinar where somebody used Slido. I've not used it as a presenter, so bear with me if I don't get this right. But I think it is a nice way of trying something different in an online space that we probably wouldn't do in a physical webinar. or in a physical webinar, I can't even talk, in a physical meetup, obviously. So, with that said, I'm going to stop sharing this screen so you can see our faces for a moment being. And I will switch to the Slido one in a minute after those of you who do want to play with it had a chance to enter something there. Maybe in the meantime, I can see here on my screen a document where Jenna has tried to group the questions, and let me answer them because they are flying through. So, in the getting ready part, there was a question that says, I tried Rust too, and what I did not like is the slow build with cargo. Is the way to optimize from your experience? And I don't think there is a way to optimize it. Don't do a release build, do the debug build that is faster because the compiler doesn't have to optimize. And on the other hand, I mean, it is incremental. So if you are doing test-driven development, the first time you get the full hit because it compiles all your dependencies and the transitive dependencies. But generally with the normal code base, at least in my experience, the compiler doesn't have to compile everything again, but only small bits. It is a general problem that I know. I know that there's build farms for C++ even, and I know from a friend of mine who works in the gaming industry that he told me that they sometimes make changes that they know are wrong, depending on which header file something is in, because they can predict in their mind already what changing the header file will trigger as a recompilation step, and they choose something that is cheaper. This is a problem in these languages, but I don't know a way to optimize it, other than buying an even faster computer, I guess. How well would Rust integrate into Microsoft C++ libraries, for example, to decrypt files? How well would that integrate with Java programs using the tool written in Rust? From Java, I guess you would have to call it as a native function. How well does it integrate with C and C++? I can't specifically talk about Microsoft. I did this on macOS and Linux, and it was fantastic. I mean, obviously, Rust was created by Mozilla for Firefox, and they are not rewriting Firefox in Mozilla from zero. They are gradually moving the code base from C++ over to Rust. And the C interop is fantastic. In Rust, you can just call a C function as if it were a Rust function. You can even do the following. Rust has annotations. I didn't show you this. You can annotate language elements like the structure definition, and you can say, dear compiler, please lay out this Rust structure in memory like the C compiler would do it. And that then means you can pass a reference, also known as a pointer, to a C function, and the C function can fill in the structure, which is then returned to Rust. So that worked really, really well. One thing I haven't tried is interop with C++ and Swift, because both of them use, of course, some name mangling. The names that the linker sees are not the same that is in the source code. I'm not really sure how Rust deals with that. If worst comes to worst, you could probably, I guess, always write a little wrapper in C around it, but calling C functions was completely painless for me. Of course, you're giving up all the safety guarantees, and in fact, in Rust you have to write, there's a special keyword called unsafe. You have to write unsafe curly bracket, then that code, and then you close the curly bracket just to say, compiler, forget about this, look away, I'm doing something here, because the compiler can't know what the C function will do. There is a lot of tooling in the Rust space to show you how much unsafe a library uses and so on, because of course that's a big concern. There was a question about big numbers. Oh, I guess with big numbers, Ali, when you asked the question, you meant numbers that are not unsigned 64, but really big. It's not an unsigned 64. I'm 100% sure there is a library around that. I'm sure there's probably multiple libraries around that, and I'm sure you have to cast it or even call functions to get one of those big numbers into an unsigned 64 in a safe way. On performance, there was a comment, amazing performance. Was it also compared with C, C++ performance? No, I didn't do this because I really didn't want to write this thing, simulation again. I've written it in Clojure and Rust. The Clojure version, to be totally honest, I have a sweet spot for Clojure. That was very enjoyable to write. I really loved the Clojure code. And it wasn't quite as enjoyable in Rust. And I know, and I've done enough C programming in my life, I know I would really hate to re-implement that in C. And this is a hobby project, and I really don't want to write 10,000 or maybe 20,000 lines of C code. I have, if you look me up on the internet, and if you look at my GitHub, my personal GitHub account, you can find actually the source code I used for the talk today. It's called Krelinor, but if you search it, or I can put it into the chat later, you can see the Rust code and you can see whether you want to write it in C. I certainly have no interest in doing that, but I do think, and that's why I decided to include the example from Brian, the dtracer guy, because he did this. He really, don't be fooled by the JavaScript bit. He really compares C and Rust because he had rewritten all the loop that is causing, like, that is taking up all the compute time. He rewrote that in C and compared the Rust performance to that. So now the questions are changing. So at some point I'm wondering whether I should switch over to the reading the chat directly. I'm going to stay with what I'm seeing in the document here. Are there any nice graphical user interface libraries? Honestly, I don't know. I have done some web programming that worked reasonably well. There's a number of different web application frameworks that allow you to return HTML and JavaScript. I guess what you could do is you probably write a React or Angular or Vue application and then use HTTP endpoints. The library I used was called Gotham. This is not the most popular one, but I did like it by far the best because it was the most testable of the web frameworks that I evaluated. There's a number of different ones. Here's a question by Tobias. How mature are the libraries? I must say, I found them very, very mature. I was really impressed by the quality of the libraries. Sometimes the documentation is a bit terse, even for somebody as an experienced developer. It sometimes feels a little bit theory heavy, but you could see that the people who wrote the libraries knew what they were doing. And again, that was in stark contrast to many of the libraries I've seen in the JavaScript world, where somebody who really hadn't thought things through creates a 10-line JavaScript piece on GitHub and that becomes the widely used library. That was very, very different. Then again, I've not programmed that much in Rust, so I don't know the overall footprint, but the core standard libraries you come across, they felt really mature to me and also designed by people who, based on my personal experience, knew what they were doing. With a language as complicated as Rust, do you run into confusion when developing on larger teams? Yes, because, I mean, I haven't done it, but I can easily see that people, that in a large team, that there's multiple ways of doing the same thing, that people would do it in different ways. I guess that depends on how you structure your code base. If you're doing smaller modules and have, say, pair programming with collective code ownership, then you probably quickly settle on an idiomatic house style, like how you do it in your team. If you work more in isolation and through pull requests, I can foresee that the styles will diverge. This is clearly something that the designers of Go have highlighted, that they really wanted one way and one way only and very simple. That's a very different approach. Rust and Go, despite that they're often used or often talked about together, are very different programming languages, completely different in their design choices. Many of the trade-offs are exactly going in the opposite direction when you compare the two languages. Error handling. There's a really nice way of doing this. I can't go into this. It does use the options and has some really nice syntactic sugar. So you don't have to do exceptions that you always catch at the top level, but you also don't have the tedious Go and C like one where you basically have to check the return value of every function. Again, I would have to show you code which I haven't prepared. Oh yeah, we talked, Sarah asked, have you tried writing a web server in Rust? Yes, I have done it. I can wholeheartedly recommend Gotham, like the Batman thing, but I know there's also other frameworks out there that are also popular. And then the last question that I can see in the document that was copied over is, oh yeah, interoperability between Rust and C is very good. C++ is possible, but considerably more effort than C. Okay, that's what I suspected because of the mangling. At some point, I've done a fair amount of programming for macOS and iOS. At some point, I do want to try to see whether I can write an application that runs on an iPhone. I want to write it in Rust. And for that, I would, of course, have to solve writing the core business logic in Rust and then calling to Swift for the user interface bits. And that is possible because they use the same compiler. If I ever get time to do it, I'll definitely write a blog post about the experience. So I'm going to go at a couple of questions from the chat, which you can also see. There's a comment by Matt saying that the type system is important and huge too. Yes, have a look at the type system. Like I said, I mean, Rust is a big language. It's really tough to pick a subset and try to give you an impression of which is what I tried. I didn't talk about annotations at all. It has a really nice way of allowing you, as an extension builder, access to the abstract syntax tree at compile time to generate some specific code. This is how the annotations are working. This is beyond the macro system I've seen in any language. I've done some really crazy things with the C preprocessor. I recently wrote variadic macros, and this was definitely not pretty. And to me, the approach that Rust took with the macro system and the annotations and how you can access the abstract syntax tree, that really, really stood out. But again, this is quite an advanced topic. I think there's a lot of good talks about this. There's one question that I'm going to answer. For fast development lifecycles, some languages have a REPL or even hot reload. Rust does not have this. Rust is a compiled language. It doesn't have it. It's just the way it is. So maybe what I'll do is, now let's try this experiment. I have stopped screen sharing, I guess. What I will now do is I will present. No, this is not working. Sorry. Present on another screen. I'm making this full screen. And now, if I find Zoom again, I'm not sure whether you can see this. So 68 people have taken part in the poll. And what we're seeing here is that 41% of you, as one of your top languages, use Java. You can read. I'm just going to scroll through. I've not seen these answers myself, obviously. See a lot of JavaScript, TypeScript, Go. Curious about other language? Maybe you can type it into chat. Scala, Kotlin. Okay. So we have an audience that is quite strong in, I guess, current web technologies, Java, JavaScript, TypeScript, Python, I guess, from a machine learning perspective. Some Go, but we don't have the hardcore C++ programmers that are looking for an exit. Ah, Clojure, yeah, I love Clojure. Julia and Perl, interesting. And only one iOS developer, or 1%, sorry, 1%, but I think that equals to roughly one person in this case. And nobody doing Objective-C, who would have thought? Okay, you can keep posting that, and I think as a participant, you can also see the answers from each other, right? So this should stop the sharing. And maybe let's have a quick look. This one, oops, no, sorry. I need to practice this a bit more. One second. Ah, sorry, I need to click here. Okay. And, oh man, this is unfair. So here we go. This is now the ideas section. I hope you can see this. Yes, good. Okay. So what are you considering Rust for? Embedded programs. So I wasn't the only one here. Learn something new is also a nice answer. And we can see, oh yeah, that worked as I was hoping. So we can see some thumbs up here. So good few people are interested in embedded programming. Learn something new. I also think this was the reason why I did learn Rust 2 years ago, in addition to the interest in embedded programming, because it felt like a really modern language. I had briefly looked at Go and it felt like, okay, if I ever need Go on an engagement with one of the ThoughtWorks clients, this looks easy enough. I can probably pick this up in a week or two, especially when I pair program with somebody else. But Rust seemed like it would give me intellectually something that I hadn't considered before. So it felt, it felt to me conceptually more interesting. Oh, jumping to the top, WebAssembly here. I don't know how many of you know the technology. This is something that allows you to run different programming code written in different programming languages in the web browser. I'm personally quite in favor of it. I'm reasonably competent in JavaScript, and I'm not really a great fan. And I think given the history of JavaScript, I think they did a fantastic job in the 2 weeks they had in the middle of the 90s. But I think the the compromises that were made at the time are really showing these days. And I don't think you can really argue that it's, by any stretch of imagination, a really advanced and great programming language. So yes, I also hope that we will see a future where WebAssembly becomes more widespread and we can then write web applications. Because let's face it, as the browser has really become a platform for writing application, I rarely, at least in the work I do with ThoughtWorks, I rarely see code being written in, like, say, in an environment where we are creating a Windows application, like the Windows Presentation Foundation or anything. On mobile phones, we still see native applications, but for most cases, we are either writing big websites or we're writing internal applications that are also running in a web browser. So yeah, I'm quite interested in WebAssembly. Memory safety, yeah, I can relate to that. Curiosity, always a good reason. There was always, what was it? Somebody said you should learn a new programming language every year. I agree. Forces me to think more deeply, yeah. Curious. A CLI tool, yeah, that's actually a good choice for a CLI tool because Rust does compile into single binaries. We just had, we put the final touches on something called the ThoughtWorks Technology Radar, which we publish twice a year. It is not out yet, it will come out in the middle of May. It is now in the translation stage. It won't get translated into German, this is too hard, and you all know English very well. But we were just writing a blip about a new tool called GOS, which is similar to server spec. And server spec is written in Ruby, and people have complained that if I want to write this tool, I have to have a Ruby environment. And of course, GOS is written, not of course, but GOS is written in Rust. And that means I have a single binary I can run and it just works. That's a really excellent choice. In all fairness, you can do the same thing with Go also, because also Go creates individual binaries. Scripting fractals, yep. Although I hear these days you're doing fractals on the GPU, and I'm not sure how you can write shaders in Rust. Intel SGX, I don't even know what that is. WebAssembly. Rust must be great when you're coming from a C, C++ world. I agree. There's an initiative. Remember I mentioned initially that, that there's some safety standards in, for example, the automotive industry. There's a lot of certification required. You can only deploy software into safety critical environments when you have certain certifications. And there's a company that is mostly based in Berlin called Ferris Systems that are now beginning to try to get a whole or like a reasonably sized subset of Rust certified in such a manner. And when they announced that on Reddit, there were a lot of people who were commenting on this and saying, I work in the embedded C and C++ space, please do this. There was even somebody who would do something with a space program, like a real space program, and said, yes, I can't wait for the day when we can leave C++ behind. But again, there are certain steps that need to be taken when you're switching. Okay, I'm scrolling over that, as you can see. Game dev, interesting. I think that could be a reasonably interesting area. I can't say at the moment, because I don't know the gaming industry well enough, because I know they have strong middleware like Unreal and Unity, where you can use C++ or C#, for example. But of course, certainly for something like writing actual engines, which is really complex code that needs to live for a decade or more, I can definitely see Rust being a good choice. And this is to me also, in many ways, a sweet spot of Rust. If you're writing something small, that is like, say, 5,000 lines of code, maybe 10,000, that has a half-life of, say, maybe 5 years, because it's a microservice, it's going to get replaced or something. I think in such cases, Go is probably also really a good choice. The Go programming language, because it's simple, it's easy to learn, it doesn't have the same levels of abstractions, it doesn't have the power that Rust has. But for these solutions, it's sufficient. If, on the other hand, I'm writing an engine for a games program, if I'm writing something large, like a renderer in Firefox, if I were the people who are looking at the future of Excel or Photoshop, like code bases that are by definition large and that will have a long legacy, that will not get replaced, then I really, really would not go with something like Go, because then the lack of abstractions will completely hurt you. So yeah, for games programming, I can imagine that that is an interesting choice. As a Scala alternative, I'm not sure. Interesting. Okay, cool. So with that said, I'm going to have a brief look once more at the chat to see if anything new. Seeing a lot of things. Thank you also for listening. Bash. Yeah, Bash. Dart. Yeah, I thought about including Dart, but I thought it was very niche. Oh yeah, of course, and you're totally right. Goss is of course not written in Rust. Goss is written in Go, hence the name. My fault. But the thing that I said applies. It is a small command line interface, and you could have written something like Goss in Rust. Apologies. I was a bit in the, yeah. Thank you. Goss is written in Go. There's a comment by, yeah, you can see the comments, right? You can see that. Ah, there's the person who talked about Scala with Play and TypeScript. Ah, okay. Yeah, the question for web development, that's the eternal discussion that is happening. And we just had that in the context of the technology radar also, again, this time around Node.js. At what point in time is the performance in a web context really compute bound? How often do you have compute heavy workloads and how often is it IO heavy? And then I think it depends more on the programming model. If you are in this more, in the programming model that Node.js pioneered in the web world, in this more event-driven model, or whether you're in the thread-based model that Java used to use until, I don't know, 2015. Of course, Java has also changed. So I'm not sure whether, depending on what you do, of course, in your web application, if you're compute heavy, I think it's probably a good choice, but also don't underestimate in general the performance of the JVM. And think also about how productive you are. I would still argue that if you are simply implementing a number of functions, you probably can do that more quickly in something like Clojure, Java. Kotlin is a big contender that we use a lot for the server as well at the moment. You are probably quicker implementing, and then you have to make a balance between how expensive is your programming time versus what is the runtime cost. Of course, if you're writing an application for iOS, Apple makes the choice for you and says, dear developer, you will suffer a little bit. And Swift does make you suffer, trust me, because it will make us, as the compiler providers, create more efficient code, which is really good for our users because the application uses less CPU and therefore the battery lasts for longer. But as I said, if you're writing a web application, it might be easier to just add a few more virtual servers and scale out horizontally if it makes the developer experience more productive. Because in Rust, it is really not as simple as in many other languages. So if you don't need the benefits of Rust, if you can't articulate why you need Rust, you might want to choose something different. As I say, as somebody who loves Rust. But that is probably also an indication as to why Rust is loved, because it is really a cool language. It is quite fun to work in. It is quite powerful. You really have that feeling you have a powerful tool at your hands, but at the same time, it is not easy, and the niche or the area in which Rust is the best choice, arguably there's always some arguments, is not that big. It is not such a universal language as, say, Java, for example. Okay, we are at the end of the time. So thank you very much for listening. Thank you for joining at an evening before a long weekend. Much appreciated. If you have further questions, if you are interested in the code, if you want to, as I said, I'm a Rust beginner. If you want to comment on the code, let me know. If you look for my name, you find me on GitHub and you can see the code. Thank you very much.